Inside this episode, using a modified military radar for weather research, improving lasers for defense and combat, and refining tactical and technological methods for tracking nuclear threats. Hurricane Point, a popular stretch on the California highway in Big Sur. Here, tourists snap pics of the scenic view. Whales breach the water to communicate with each other, and an unusual sight, a large radar on the back of a transport truck. It's part of a study conducted by NPS's Center for Interdisciplinary Remotely Piloted Aircraft Studies, or CIRPAS for short.
Today we're using the mobile radar truck, which is a phased array system supporting an experiment by the University of Miami. They're looking at atmospheric conditions of the stratus clouds typically found off the Big Sur coast.
And we were looking at the physics of the cloud, and we were utilizing chaff and salt to be able to both look at the cloud and the salt to nucleate bigger droplets and initiate drizzle.
The radar itself is an Army phased array system that we acquired from the Army back about 2000. And the main purpose was that everybody in the research community, the scientific community, wanted a mobile phased array radar.
And so over the past 10 years, we've modified the radar to allow it to do meteorological work, and that was done in conjunction with the University of Oklahoma, Hallie Bluestein, and we went out storm chasing with them and others to be able to incrementally develop the software and other tools that the radar needed to be able to provide scientific capability.
We've taken the military system, we kept the military radar portion of it, and we got rid of their processor and their control. We have our processor here to basically collect and process the data, and then we have our GUI. All the controls for the radar is done from the laptop. So we've turned it into a very simple system. Grant you, this is not doing its military function. So it's doing something else completely different that it was designed for.
I'm used to working on the Spy-1 radar on the Aegis platforms. So coming here, working on a land-based radar is different.
Previously, I was a Slick 32 technician on the CVN-69 anti-ship missile defense radar system. Navy uses a lot of the older radars, so it's not anything new to work with something that appears to be old or outdated.
Definitely learned a lot about meteorology. Definitely a different aspect of using a radar for sure.
I'm sure everybody has seen the Weather Channel or the local news and the Doppler radars and the data they collect to display on TV. A lot of those systems take approximately maybe 15 to 20 minutes to collect the data, but we can collect an entire volume in about a minute to a minute and a half.
It's very fast. It can scan the entire storm in about 5 seconds.
What we're looking for is basically very typical data return that we would see on any PPI. We can see the aircraft, we can see when the aircraft has expended the chaff and when the chaff starts blooming, which the bloom rate and the drop rate of the chaff will depend upon, once again, the atmospheric conditions.
Twin Otter's our primary research aircraft, and we've made quite a few modifications to it. That main inlet on the nose and hard points on the wings. We have ability to drop things from it like chaff or sonar buoys. We carry quite a bit of instrumentation in the fuselage of the aircraft. On the wing, there's a cloud physics and aerosol combination of probes. So these probes, they measure droplet number and size, and also aerosol. And that gives us an idea of exactly what's making up the physics of the cloud. So what's the size, the number, the composition, what's affecting those droplets in the cloud, all can be measured from those instruments. We do about 3 to 4 science missions a year with the Twin Otter, sometimes more. Mobile radar, maybe 1 or 2 missions a year. Primarily for the mobile radar, it's a severe storm radar. X-band, you primarily get the best bang for your buck for the science, looking at meteorological phenomena that have a lot of scatter. A big thunderstorm has a lot of cloud droplets that will scatter X-band back.
Currently downloading the data that we have collected over the past 4 runs. Today was a full run, lasted about 2.5 hours. So we have about 8 to 10 hours worth of data to download. And hopefully in about the next hour and a half, the data will be downloaded. We'll send it to another person who will transcribe it for the University of Miami, and then they will take the data and process it.
And that's one of the things I think showcases what we can do at NPS CIRPAS, which is being both a military organization, part of the Navy, and a university. We can go into the military inventory, get some piece of equipment that's not being utilized, and then take that equipment and modify it to give it a new capability, which is involving the sciences. And so that radar is not really accessible to anybody else in the university world except for us. We can go into the inventory, get it, modify it, and then work with other universities to bring a whole new capability to bear, which allows new types of measurements that just weren't possible before.
Not long after completing this mission, CIRPAS went out on yet another experiment, this time supporting NASA collecting pollution data in Southern California. Up next, scientists and law enforcement team up to simulate a nuclear threat in the San Francisco Bay.
Across the bay from San Francisco, Alameda Island, a former naval facility, now home port to Navy cargo vessels. On this day, it is a testing area for maritime interdiction operations and weapons of mass destruction, intelligence, surveillance, and reconnaissance. On board the MV Cape Orlando, participants and observers gather at the morning meeting. NPS professor Alex Bordetsky leads the multi-part field experiment.
How to put together new counter-WMD-ISR operations as they unfold based on the small craft threat in the area or cargo ship delivery of the threatful material or the other means of illicit material trafficking into the area of our concern. That's basically the scope of our experimentation.
The experiment is supported by Lawrence Livermore National Laboratory, technology firms, law enforcement, and defense agencies. The plan is to simulate a nuclear threat at sea and on land, and to use an assortment of technology and tactics to detect and track radioactive materials. A large laser spectroscopy system rides in the back of a rental truck. Operators roam the port, scanning nearby warehouses for radioactive material.
What are you shooting?
The fire exit sign inside the building. There's a white
Fire exit sign on top of it. Oh, yeah.
So may as well be able to interrogate the inside of the building if we can, right? So I shot the door, no threat. Naturally shot the that sign, no threat, and I'll shoot the frame again. I'm actually shooting, since that door's open, I'm shooting way above everybody's head.
The system's boxy design, basic laptop, and video game control pad belie its true capabilities. One laser is triggered to induce plasma on a surface of a target. Another laser stimulates amplified emissions from the plasma that is detected by one or more spectroscopes. The gain induced by the second laser detects traces of explosives and other substances on surfaces.
You'll generally fire 3 times and then you'll get a reading.
It gets a hit.
PC.
The exact range and amount of material that can be detected by the system is held secret. At sea. The Marine unit of the San Francisco Police Department track a small boat suspected of carrying nuclear material. The small boat, in this instance, a Coast Guard auxiliary vessel.
One course here, just pick a heading and hold it for a minute. We're just going to test them real quick.
David Trombino, of Lawrence Livermore National Laboratory, explains.
So what we're seeing now is that on the target vessel we have detected some radiation. You see it continues to go up, and it's turned red, saying it's above our significant trigger level. So now we're seeing this peak in the energy spectrum that tells you information about the source. That's something that by doing an acquire, we have some data we can send to reach back, and the way this is rigged is that as soon as it saves that spectrum, it's actually doing a 1 minute count, and by being close we're getting all the information. As soon as the 1 minute is done, the spectrum is automatically posted on the observer's notepad.
Observers reviewing the data at the operations center would coordinate among subject matter experts and advise the boarding team on how to handle a search. Intrigued by the results, Sergeant Keith Matthews coordinates a series of maneuvers to observe different detection results.
That's going to be the training tool right there, is to say, with this size of source, we saw we had to get a distance of no greater than X to be able to detect properly, or to get the readings we needed.
Underwater searches can often be time-consuming, not just because of low visibility and other dangers in the water, but because of the inability of communicating without the need for the diver to resurface. Until recently, doing so electronically has been seen as untenable. However, after numerous tests, Bordetsky and his team have shown it is possible. The diver, using a wireless device, can send messages and pictures via Bluetooth to the hardwired computer seen here in the red box. The buoy contains a computer hardwired to the second computer placed underwater. An operations tech, either shoreside or remote, would transmit messages and pictures to the hardwired device. The hardwired device relays to the underwater computer, and that computer sends the data via Bluetooth to the diver's wireless device. The method would work in reverse as well. If such a method were perfected with little to no lag time, it would significantly aid in decreasing search times and increasing safety for divers. On this occasion, they also plan to test LEC wire, which can illuminate and transmit data simultaneously.
The basis is electroluminescence, but what we have going on here is an LEC. It's a light emitting capacitor. So you can have very, very long lengths that are deployable quickly, easily, to put a defended pathway down or to get people to ferry lots of people out along it in a hazmat situation. They can run along the line, and the responders can therefore work on the people that are down, that truly need their help. Another advantage to this is that any form of data, comm, control, power, conveyance, can be sent down the middle of this light because the light lives in a cylindrical aspect around it.
A search of a large boat would require numerous pieces of technology to quickly detect a threat. A land ROV would be used on deck. An underwater ROV would be used to check the outside of the hull. Another effective tool is the gamma ray germanium imager.
This is an image taken of a cobalt-60, a cesium-137, and a uranium source. And in about 3 to 5 minutes, we were able to localize the cesium and the cobalt-60 because they have fairly high energy gamma rays. There's fairly radioactive sources. We can see the uranium, we were able to localize in about 10 minutes. This software also lets us look at the spectral information as well. And from this, we can actually see the unique radiation from each of the isotopes. We can see the cesium-137 along with the bismuth-210 and some radium lines as well.
There we go.
The U.S. Coast Guard serve as the boarding team and make their way through the vessel. Along the way, members test the communications system using ATAC wearable mesh and relays placed at key points throughout the ship. In the engine room, David Trombino hides the radioactive material.
So here's the cesium source, and over here is the cobalt source. A rock in here. This is the smoke detector.
The boarding team arrives in the engine room and attempts to contact the bridge. The boarding team must test the room with a radionuclide identification device. They get an instant response.
You look surprised.
but they have trouble narrowing down where the threat is located. Notably, the brightly colored containers do not stand out among the various worn signs and mechanical equipment. The nuclear material is effectively hidden in plain sight.
Oh, it's you. That's you.
Maybe it's.
Are you?
Guarantee there's nothing on her.
In any case, searching by sight is not the primary objective. The boarding team must follow their training, use the device, and ascertain the location of the radioactive material. Because the cesium and cobalt are so near to each other, the radionuclide identification device gives back odd readings. Trombino reassures the team of how to use their equipment to detect the threat. He shows them how a smoke detector can produce a false positive, and he shows them the location of the cesium and cobalt. Much of what Bordetsky's team is attempting is still in the experimental phases. However, gaining the interest of local law enforcement and the Department of Homeland Security, it appears such maritime interdiction operations will remain a crucial learning tool.
And the Navy, for the first time, will deploy a solid-state laser aboard USS Ponce. Officials say the laser program is central to deliver advanced capabilities to forward-deployed forces because it complements kinetic weapons to create a better layer of protection.
From science fiction to science fact, from dance clubs and CD players to guided missiles and ray guns, lasers have changed our way of life. But great advances also come with great hurdles. A laser research group at NPS has been working to solve the technology's limitations. One professor explains more.
My name is Keith Cohn. I'm a research assistant professor in the physics department. And part of our research is looking at how weather impacts the performance of a high energy laser. A laser is a device that produces a beam of coherent light, and it's different than your typical flashlight in the sense that the beam of light is highly focused and it's at a pure wavelength, at a pure color. So a high energy laser is the same basic principles of a low power laser that you might have in a DVD player. So you have to have some sort of gain medium that you have to energize in some way, and you produce, again, a beam of light that has many kilowatts of power in the light beam. So that's powerful enough to burn materials, to damage materials, to melt the materials. To get to the point where we can start damaging a target, we have to send that light beam from the ship or from the source to the target itself. And of course, the target can be some distance away from the ship. So we have to propagate that light through air, through the atmosphere. And depending on what the weather conditions are, it could be a very turbulent day, which tends to cause the laser beam to break up. Or it could be a hazy day, which causes the light to scatter away from the core of the laser beam. There's different conditions that can degrade the laser before it reaches the target, and it's important to understand how the laser degrades. An analogy might be that if you send a laser beam through a piece of wavy glass, that can cause the beam itself to kind of break up and be deflected at different angles. If that glass is a little bit cloudy, then again that can scatter the beam as it's going through that piece of glass, and the atmosphere acts much the same way, except it's over a much longer distance. So the atmosphere can cause the beam to wander, and it can cause the beam to break up, and it can also scatter the light. And so what our research has done is characterize the laser in different weather conditions, in different levels of turbulence, different levels of haze, different levels of rain, and across a wide spectrum of wavelengths to determine what the effective range of these weapon systems are. And so we know we can calculate how much power we need, how much energy we need to deposit in order to melt a certain volume of material, and then analyze the laser system in these weather conditions to see whether it crosses that threshold or not. So one of the things that we looked at was how turbulence affects the laser performance. And so in this plot here on the y-axis, we have the irradiance of the laser on the target at a range of 5 kilometers. And this red line represents the sort of melt threshold that we need to exceed in order to affect the necessary damage on the target. On the horizontal axis, we have the wavelength of the laser system, and we can see that different wavelengths are affected differently by the turbulence. And the different levels of color, the light represent different turbulence levels. The light blue represents very strong turbulence, and the dark blue represents very weak turbulence. And so we can see that at a target range of 5 kilometers in strong turbulence, we don't exceed that melt threshold, which means that when strong turbulence conditions prevail, we would need to allow the target to be a little bit closer to the laser system before we engage that target. One of the things that we needed to do in order to estimate the performance of the laser system in different weather conditions was develop our own code that would allow us to scan across millions of different weather parameters and laser parameters. So in order to do that, we need to define what sort of weather conditions we want to analyze, and then we need to determine what the optical properties of the atmosphere are, and then we plug that into our code and scan across, again, millions of different parameters to estimate the various figures of merit for the laser system. So one of the advantages that lasers bring to the table is their per cost engagement is very low. So they're electric weapons. As long as you can provide the necessary electrical power to the laser system, then you essentially have an infinite magazine. So this is, of course, a huge advantage to engaging various targets, numerous targets, relative to conventional weapons, which, of course, are quite expensive per engagement. Another advantage that lasers bring over at conventional weapons is that they're highly focused and precise, whereas conventional weapons, such as bullets, they tend to spread out as they're traveling toward the target. And that really allows us to deposit that lethal energy into a very small area, a very precise area. Another very attractive feature of lasers is that it delivers that lethal energy essentially instantaneously, so at the speed of light. So what that means then is that it's difficult for targets to maneuver out of the path of that lethal energy because, again, that energy is delivered instantaneously. So what I find particularly interesting about laser physics in general is the wide variety of technologies that can be used to create a laser. So you can have, again, a solid-state laser, which uses a solid piece of glass or crystal to generate the light. Or you can use a semiconductor in the case of a semiconductor laser. Or you can use free electrons in the case of a free electron laser. All of those technologies produce a high-quality coherent beam, a laser beam, but they generate it in many different ways. There's a rich body of physics associated with each of those kinds of technologies.